All right, so we're gonna finish earlier this morning session, so you have a larger break to have lunch and rest a little bit. So hello, Dimitar. You are the next one. You are gonna talk us about blockchain meets quantum. So let's see what is this about. You are a distributed ledger and technology and IoT expert at Cefri. So welcome and thank you very much for being here with us. The floor is yours.
Okay, thank you, Carmen, for the introduction. Can you just confirm that you're seeing the screen? Okay, perfect. So today I will talk about something way different that we saw in the morning. We'll speak about quantum development and quantum blockchains, something that is interesting and something that is rising slowly to us. I'm going to explain a project that we worked on. It's QKDN quantum secured blockchain. It's quite interesting. So first of all, just let me introduce myself. I work in Sheffield for almost 5 years, where we do innovation and design of disruptive technologies. Especially a member of the blockchain lab, where we are working more than 20 technologies about blockchains. We're also part of some consortiums, national networks of experts, board of financial blockchains. We also done a lot of projects regarding blockchain for European Union, for companies. So we're quite experienced in doing this. So first things first, let's start with what is quantum computing and why it's important and why it's interesting to know this stuff. So in traditional computing, we have we have bits, we have zeros and ones. So they're basically transistors inside that are just acting like ramps, like it's going to let the information flow or no. So we have either we have information, or we don't have. And in quantum computing, we have qubits. So it's something different from the traditional ones. And I'm not going to bore you in technical details and stuff because it's not that easy. And also I'm not an expert in quantum computing. But these are just the things that you should know. So we have two interesting things that we have to know. One of them is the superposition and one of them is the entanglement. The superposition is basically a quantum system that can be multiple, it can be in multiple states in the same time. So it can be 0 and 1 in the same time. And that is a game changer because we can speed up the things. And entanglement is something discovered by Einstein, and basically means that two particles can, no matter the distance between them, can be entangled. And if one of them is changing, also the other one is going to change. And that is also called the spooky action at distance. It's quite interesting stuff. And you can see here the comparison between the classical computers and the quantum computers, where we have the bits that can be 0, 1, and then we have a qubit that is actually spinning. And once when it's going to be polarized, it can get that one state that is having. So why quantum computing? Why this actually matters and is actually affecting also the blockchain technology. As we know, Moore's law is something that it was pretty much accurate all of these years. And we can see that from the starting of the transistors and computers, we have doubling in computational power every 1.5 years. But what happens when we are going to get to the point where we cannot that much increase the density of transistors? It's called Silicon Dark Age, and basically we're pretty much there. And it means that the powering and the computational power cannot scale anymore. So we have some physical limitations that we cannot scale beyond that. And that is quite interesting because, as we know, as humans, we want to do things faster, we want to do quicker. So in some point of time, we're not going to be able to do that. So that is why we need quantum computing. And quantum computing is still in early stages, but it's slowly going in the commercials. So basically, it's all about the speed. So in normal computers, something can be done like very slowly. We have some problems and issues in computing some tasks that actually cannot be done or require a lot of processing power and years of doing, so we can solve that. But with quantum computing, we can do that pretty much quickly. And something that is also very interesting is called quantum supremacy, that actually Google in 2009, if I'm not wrong, they basically announced quantum supremacy. That means in general that now we're able to solve with quantum computers tasks that are basically requiring to be done with supercomputers years and years, like 150 years it's required for that task, and with quantum computing we can solve that task in a matter of seconds. In these normal stages that we have quantum computers right now, they cannot replace the conventional computers. They're basically requiring spatial rooms that are built, that are quite big and require like absolute zero temperature to that they can actually work. And this is also something interesting, that it's a blockchain adoption curve. So basically, blockchain is not that much mature technology still. And this is basically a curve that maybe we can discuss it later. We have to know where we right now. So maybe in 2016, 2017, we are just early adopters of the blockchain technology, but especially these 4 or 5 months, a lot of things changed, and probably we are maybe in the early majority, but it's something that is, it's something for discussing. So with this, basically, how we're moving and how we're going more on this curve, the blockchain technology is going to change a lot, and it's going to that mass adoption, and we can see more use cases and more commercial use. So this is just an encouragement for you guys that you're on the right path. So by choosing a blockchain technology in your use cases is something that is very good choice. So how is actually related blockchain to with quantum computing? As we know, by design, by now, blockchain is unpenetrable technology. So no one has ever hacked blockchain. Yeah, we saw some hacking, but that is on a wallet side, but not on the network. And this is something that we done. It's like a matrix that we can see all of the possible attacks on the blockchain technologies, and the likelihood that is going to happen, and the impact on the whole blockchain network. So with QKD, I will explain it later, is basically a quantum key distribution. It's a part of quantum computing. It's covering basically this red space here. So Grover's algorithm and Shor's algorithm are you can read about that if you want. In the end, I will send you materials if you want. It's about like now if someone is using quantum computer in the background, we are not able to notice that. And basically, mining the blockchains, we have consensus mechanisms. With quantum computing, that's very, very easy to penetrate and to basically to make damage. And for now, we don't have that much security about that. So in the other end, maybe there is someone that is using quantum computing, and for example, imagine if he's mining, it's not going to be fair, because with all that processing power, he's just going to take all of the pool awards, and then you can imagine what can happen. Also, with with merging the blocks and making them into a chain, it can easily, because they're connected with hashes, and then we can easily do hash collisions and stuff like that. So there are basically two algorithms that are preventing that are actually can happen with them. Down you can see basically what's the difference and how basically we can improve the security of blockchains. When we started this project, basically there is no quantum blockchain, there is no that much information, and the only thing is basically papers. There are like 2 or 3 approaches to this, and one of them is basically a whole quantum blockchain that is quite interesting, and it's quite complex. And we have digital quantum cache, we have entanglement in time. It's also interesting approach. So there is not that much products that are out there. We worked on a project that is called QSecureNet. Basically, we are probably one of the first that sent quantum keys in blockchain, via blockchain. And basically, quantum keys are just ways of sending keys between 2 parties, for example, Alice and Bob. And they're unconditionally secure, because there is no way that you can actually eavesdrop the communication, and it's raising the security of the whole system a lot. It's a Nova blockchain application based on the secure network platform, and we made a use case for atomic transfer that is built in Algorand, so it's quite interesting. I will explain you later. The project was done with consortium with partners. Basically, Politecnico di Milano was doing the apparatus that was actually creating and sending that quantum keys. Then we have Telefonica and UPM and Italtel that are doing basically deployment of the real optic network. So this was done on real optic network, not dark network, where you in dark network you're just using fiber optics just for that purpose. We used real optic network in Madrid, and we as Sheffield, we done the quantum secure services where we done the technology scouting, where we developed the application, and we increased the security provided by the QKD. In a nutshell, quantum key distribution works like basically like every other, but it's reliant on quantum mechanics. So using the quantum mechanics laws, we're transmitting a sequences of bits between 2 points, and that is totally immune from eavesdropping. Eavesdropping is basically if someone like is spying our network or is trying to tampering our network. So it's not possible to be done that. It's done between the optical fibers, and we just use the quantum key distribution to exchange the keys between the parties, but then everything is happening through the regular network. So Alice and Bob can share a secret key, and then they can basically ensure a communication between them, secure communication between them. The QKD market is basically something a lot different. It's new phenomena, and the research about this is pretty much kept up in secret. So the most advanced quantum computer until now is the one that is made by IBM. It has 65 qubits, and that's a lot of processing power. If you want, you can check it on IBM. You can, if you want to see it, if you want to program on it, or if you want to do something, you can. It's publicly open, so you can access to it. We're the first one in European Union that we made such a thing. There is initiative also in Korea, Japan, China, USA. So it's something that is rising. This is our first product version that we done. So general availability, it was done by the end of the 2020. Some informations about the product features, the distinctive features. So the traffic fiber, we support any topology. So it's ETSI standard compliance, and it's meant for basically where we need security, like to increase the level of security. Atomic transfer is something that I suppose that you know. It's it's used in the blockchain technology, and we use this type of use case just to show that we can connect the blockchain technology with quantum computing, with quantum key distribution. And the exchange of informations, the keys, the hash time locks, and everything's are secured by the QKD. In our case, we used Algorand. It's a platform for, it's a blockchain platform that is pretty much famous. And we use that for making atomic transfer between three parties. So it's something that is required. Atomic transfer is something that is a hot topic, and it has a lot of benefits, and that is why we chose to go with that kind of use case. Basically, the atomic swaps can have multiple use cases exactly that if you want to use them, but usually we use them in index scenarios. So it's a way how to make interoperability of chains, and that can be used in financial use case scenarios for exchanges cryptocurrency, for examples, or in future possibility to investigate applications in telco and media scenarios, and basically it can find everywhere a solution. Algorand is a platform, something that we used there. It's pretty much advanced and mature technology, and it provides something more than Bitcoin. It provides smart contracts, then you can create atomic transfers, then it divides in layers. It's quite interesting platform for working on. Sorry. Okay, so, and this is just a quick screenshot just to see this is the first QKD that we send between two parties. We've done this through cloud machines, and then we were able to send one key from one machine and then to receive that key to the second machine. And basically, how was the whole process working? When Alice and Bob are going to exchange the keys, then the atomic transfer can happen. So we are pretty sure that on one side is Alice and in another side is Bob, so we can make the exchange. I think I'm pretty much done. I don't want to bore you to death with more details and technical details. So if you have some questions, you can ask.
Sure, I would have a question.
Yeah, sure.
So, like what I understood is that the are like way faster than normal computers.
I'm sorry. Can you just repeat because it was a noise?
What I said, like so far I understood, is that quantum computers are just way faster than normal computers.
Yeah.
And the security of blockchain networks today relies on that it's not possible to guess certain, like a private key, or to guess like a hash value. And so because quantum computers are so fast, it's for them it's able to guess the private key, or to derive the private key from the public key, or to derive the hash. So how are you actually doing it? Like, is there just like unlimited to be quantum proof? Do you have like just unlimited more possibilities that even the quantum computer is too slow, or how are you solving this?
So basically, how we fight against quantum computing is using the quantum encryption, something like QKD, or there is also some encryption tools that are post-quantum, so that are actually guaranteeing that they can save you from stuff like this. R3 Corda, basically, it's providing with post-quantum encryption. So another, I'm not pretty much sure that other blockchain platforms are using post-quantum. The one that I know is R3 Corda. That's the thing. This is right now just the beginning of this, because it's very, very expensive to build quantum computing. So quantum computers. So that's very, very, very difficult task, and that is why we have just a couple of them in the whole world. But if they start to evolve like a lot, then we are going to have the problem, and then we will have to somehow make post-quantum blockchains. That is why this is still early for this, but still we have to think about that, because as you said, it's with that, for example, with 54 qubits, you are able to solve some problem that actually requires 150 years to be solved with the most fastest supercomputer. Then imagine what is going to happen to private keys with brute forcing, with hash collisions or stuff like that. So yes, for now, I think there is not that much place for concern, but maybe in the next, I don't know, 5-10 years, this can be actually a problem.
Thanks. But still, so quantum proof encryption means that there are just like unlimited more possibilities, or what does it mean?
No, with post-quantum encryption, basically you're safe. So it's a different kind of encryption algorithms that can be implemented, for example, in R3 Corda, and you have pretty much bigger level of confidence that is not going to be able to be attacked by quantum computing and be broken.
So in a certain amount of time, probably. So then the quantum computer would need like 100 years to solve this.
I'm not sure. I'm not sure about that, because I think, in my opinion, that it works in another thing, because it's changed how it works. Because with quantum computing, for example, you can do brute force, you can do hash collisions, but in this case, they're providing elliptic curves, and then it's different how it's calculating.
Okay, thanks.
You're welcome. Do we have another question? I think that we don't have. So, Carmen, I think that the floor is yours.
Okay, so if we don't have more questions, I don't think so. If you do, just open your microphone. But if not, we can just conclude these morning sessions. Thank you very much, Dimitar, for this brief but interesting session. And for the participants, for all of you, we are having now a lunch break.